This is a short video on how to determine the redox number for a given element in a chemical composition and balance out simple redox equations. So in groundwater we can have redox active elements such as nitrate or ammonia, or it could be dissolved iron. We could have iron precipitated as iron hydroxide, and a lot of other, some manganese, maybe components. So in the soil, and organic matter could be in the form of elements like this. This is a sugar, but they are very complex structures. But anyway, just some classical things. And if we look at to what is the redox number of the elements in such simple chemical compounds, well, the rule is that whenever you have oxygen has the redox number -2, and hydrogen always has redox number +1. And that has to do with their electronegativity, that oxygen wants to attract a couple of extra electrons to get 8 electrons in the outer shell, and it is very electronegative, so it has a very strong propensity to draw in electrons. So the exceptions to this, the only exceptions, are when we have molecular oxygen. In here, oxygen has the redox number of 0, because actually in a compound the sum of the redox number of the elements included is always adding up to the charge of the molecule. So in this case we have oxygen actually having 2 ties to another oxygen molecule. So both of them have to have the same redox number. They're pulling equally, sharing in these 2 shared electrons each, and that gives it the redox number 2. And then there's another, so hydrogen, for instance, here we also have hydrogen has the redox number 0. But in all other components, except for what's called peroxides, for instance H2O2, things doesn't add up here. That's also slightly different. But apart from that, these are the redox numbers associated with oxygen and hydrogen. And then the rule is that the sum of redox value numbers equals the charge of the molecule. So let's try to look at these components up here. Here we have 3 oxygen atoms, each -2, so that's -6. It has to add up to -1, so nitrogen has to have the redox number of 5. We write it as a Roman value V, so nitrogen has the redox number 5 here. Over here, that's nitrogen in the most oxidized form actually, with +5. Over here, nitrogen is associated with hydrogen. There's 4 of them. Each of them has +1, so there's 4 pluses. It has to end up with 1 plus, so nitrogen has to have -3 as redox number here. Here we have one substance with a charge of +2, so the redox number here is 2, +2. Here we have carbon. We can see we have 6 oxygen atoms, -2, so that's -12. We have 12 plus hydrogen, so that means that carbon here has the value of the redox number of 0. In CO2, which is the very oxidized form of carbon, carbon will have to have a value of +4, because there's 2 times 2 minuses here, and it has to end up being net no charge of this molecule. Iron here, well, this is -2 plus 1, so this is -1. This group, there's 3 of them, so the iron here is oxidized, has to have the redox number +3. So in molecules, this is how simple molecules, you can determine the redox number of the components involved in the molecule. let's say you have a reaction you want to balance out. Let's say we have the reaction where iron 2 ions are in an environment with oxygen, and that could lead to the oxidation of the iron. We can see here iron has the oxidation stage of 2, and we know that, and that's something you know from looking at the different elements, which oxidation stages can they appear in. Iron can be appearing in as iron 3. So for instance, in this component, a solid component, because iron 3 is not very soluble. So if we were using oxygen, and oxygen here has a redox number of 0, then what happens with the oxygen here is that the oxygen goes from 0 to -2. So we write that oxygen goes down 2 in redox numbers. So oxygen number changes. Iron is going up. So whenever there's a molecule or an atom going down in redox number, it's an electron transfer. So another one has to increase in oxidation number. This case, iron is going from 2 to 3, so it's going 1 up. So oxygen going 2 down, iron going 1 up. And that means I have to have a ratio between oxygen and iron in 1 to 2 in my equation up here. Every time I have one oxygen atom, I have to have 2 iron atoms to balance out the change in electrons between the two. So when I see here that I have 1 oxygen molecule with 2 oxygen atoms, that means that I have to have at least 4 iron atoms to balance out the usage of 1 oxygen molecule, looking at the redox numbers and the change of electrons. So if I have 4 over here, I need to produce 4 of these, because I have to have the same amount of substances on either side of my reaction arrow. But so far I'm okay with the redox, but now I need to look at the balance out things in terms of charges, because I also need to end up with the same amount of charged ions that I start out with. So I have 4 times 2 pluses over here. So I need to add something like 8 pluses on the other side, and what that could be is H plus ions. So I always, in any water solution, I have H plus, or I could write it as H3O plus if I add water on both sides of my equation. But let's just look at it like this. So it is a process that produces acid. I'm still not completely balanced, because I can see that in terms of hydrogen, I have 4 times 3 hydrogen atoms embedded in this substance here. So that's 12, and I have another 8 here. So that's 20. So I have 20 hydrogen atoms here. So I also need 20 hydrogen atoms over here. And I can add always water on either side of the equation to balance out things. And if I have that, I need 10 water molecules to balance out the equation with respect to hydrogen. Now I could check, the last thing is to check with respect to oxygen, because now the things should fit. I can see I have 4 times 3 oxygen molecules here. That's 12. And I have 10 here, and I have 2 here, so I have 12 on either side. So I'm complete with this reaction. So that was balancing out the oxidation of iron with oxygen. I could, another example, look at what if I have some organic matter, and I could write this as CH2O, so a hydrocarbon. This is just a very simple representation of organic, typically distributed numbers of oxygen and hydrogen and carbon in an organic molecule. So what if I take organic matter and I oxidize this with nitrate to atmospheric nitrogen, and I know I get CO2 and water probably also out of it. So how can I balance this out? Well, first I have to look at the redox number. carbon here, as in my organic matter up here, has the redox number of 0. Nitrogen here, as I saw up here, it's the 5 plus. So carbon ends up in CO2. Here it has the value of plus 4. It's becoming oxidized. And nitrogen here is in a nitrogen molecule with no charge, so it has to be 0. So nitrogen in this case here is going down, is being reduced with 5. And carbon is going from 0 to 4, so going up with 4. So I have a ratio of nitrogen to carbon of 4 to 5. So I need 4 nitrogen atoms for every 5 carbon atoms I've got. So I could adjust my equation here saying 4 and 5. Now that matches in terms of changes in electrons. Having 4 nitrogen atoms here, I need to have 2 molecules of molecular nitrogen here to match the amount of nitrogen on either side. And I can see with respect to carbon, I would need to have 5 CO2 molecules produced because I use 5 carbon atoms in my organic matter. Now I could look at my hydrogen and balance out with water. Or first I could actually take a look at the net charge. That would be better. So I can see that I am using negative charges here, so I would be using some acid in this process. I need 4H plus to balance out the 4 minuses as I have here, because none of the products are charged. So I'm using some acid in this process. Now I could look at the hydrogen. So I have 4 here, another 10 here, none here, so that's 14. So I need to end up with 14 over here. That means 7 water molecule, and then I could check with oxygen to see if my things are adding up correctly. 5 times 2 is 10, 7 is 17. I have here 4 times 3, so 12 plus 5, which is 17 as well, so that adds up. So that's how to balance that equation. This is a simple redox equation, and this change of electrons now matches because I have a transfer of electron between nitrate and carbon. So it's really not the oxygen here that oxidizes the carbon. It is the nitrogen that is the oxidizing agent, because oxygen here has -2 in redox number, and it also do so in carbon dioxide. It also has -2. So that doesn't change redox number. What changes redox is the nitrogen that is being reduced to atmospheric nitrogen and the carbon which is being oxidized to CO2.